After having learned how a processor executes instructions, now let's take a look at memory, where all the instructions and data are stored. So ideally, this is what programmers wish the memory to provide. They wish it to be large so that there is no limit on code size and data size, and the programmers can write as large and complex applications as they want. They also want memory to be fast so that data can be accessed instantaneously and the applications execute quickly. Finally, they want memory to provide high bandwidth, and high bandwidth means that you can have fast access to as much data as possible. However, as you can imagine, there is no single technology that fulfills all of these requirements. Sometimes it's just an issue of cost, and sometimes it's not technically feasible to build such a memory. Well, if we do not have a single memory technology to meet all of these requirements, what can we do? An alternative is to build a memory hierarchy using different memory technologies. And the idea is that the memory hierarchy approximates this behavior of large and fast memory. So you do not have a large and fast memory, but the memory hierarchy provides an illusion to the programmer that there is a fast and large memory. So let's see what are the different memory technologies that we can use. So here we have some of the technologies. The middle column shows how fast these technologies are, and the final column shows the cost of building such memory per 1 gigabytes. So we have SRAM, which is very fast. You can access it somewhere in 1 to 10 nanosecond, depending upon the size of the memory. Just to give you a perspective of how fast 1 to 10 nanoseconds is, if your processor is working at 1 gigahertz, the cycle time is 1 nanosecond. So a 1 gigahertz processor can potentially access SRAM in one cycle. But in generally, it takes few clock cycles to get data from SRAM. The problem is it's very expensive. To build 1 GB of memory, you need to spend about $1,000. Now, if we put this number in perspective, an average laptop costs somewhere between or somewhere around 1000 and sometimes less. Now, if you have 1 gigabit of SRAM, your SRAM itself is as expensive as your complete laptop. So it's just not really a good idea to fill your memory or 1 GB of memory using SRAM. So SRAM can potentially be used when you need small amount of memory, somewhere in few megabytes, but not in gigabytes. Then we have DRAM, which is 10 to 100 times slower than SRAM, but it's also about 100 times cheaper. So if you want to build big memory, it's better to use DRAM because it provides a better trade-off between access time and cost. Going down, we have SSDs, which are maybe 1000 times slower than DRAM, but they are also very cheap. And disks are even more slower and even more cheaper than SSD and other technologies. So what we see here is we have different technologies which provide a trade-off between access time and cost. So we can use some of them to give an illusion that the memory is fast, and the others to give an illusion that memory is cheap and potentially large. Okay, so which of these memory technologies do you think is used to build your main memory? And main memory is the RAM in your system. So it's the DRAM which is used as the main memory in the systems these days. Okay, let's see how these memory technologies really store a bit. So let's start with SRAM, which is static random access memory. To store a single bit, SRAM uses two cross-coupled inverters. Here you see the schematic. So this is one inverter, this is the second inverter. The output of this inverter is connected to the input of second inverter, and the output of second inverter is connected to the output of second inverter is connected to the input of the first inverter. So this cross coupling holds the bit. Let's take an example. So let's say the value here is 1. So this one goes to the input of this inverter, and what you get at the output is a 0. So this 0 then goes to the input of this inverter, and what you get at the output is again 1. So this cross coupling, this feedback path, retains the stored value. Now to store this value in terms of number of transistors required, we need 4 transistors. We need 2 transistors to make one inverter and the other 2 transistors to make the second inverter. Again, the cross-coupled connection is also shown here. So this is the output of this inverter, and this output is connected to the input of second inverter, and then the output of the second inverter is connected to the input of first inverter. So these 4 transistors are used to hold the value, to store it. Then we need 2 additional transistors to access the cell, and this transistor M5 and M6, they are used to access the cell. That means whenever we want to store the value or read the stored value, we use these 2 transistors. Okay, now let's move on to DRAM, the dynamic random access memory. So instead of using 2 cross-coupled inverters like in SRAM, DRAM uses one capacitor to store a bit. And the and the charge stored in the capacitor represents 1 or 0. An example is if the capacitor is charged, it's 1, and if the capacitor is discharged, it's a 0. So you see, instead of using 4 transistors, now we use only one capacitor to store a single bit. So we probably need less area to store a value in DRAM. And also, instead of using 2 access transistors, we need just one access transistor in DRAM. However, the problem is the capacitor is leaky. It leaks charge over time. As a result, the value stored in a DRAM cell can disappear after a while. So if the value was 0, then anyhow there is nothing in the transistor, we don't have a problem. However, when we charge the transistor and if we do not access it for a long time, this charge will be disappear, and what we will have is a bit flip from a charged capacitor to discharged capacitor, or from a value of 1 to a value of 0. To prevent this kind of losses, what we need to do is we need to refresh this capacitor periodically. And how often do we need to refresh it depends upon the RC delay. That means how quickly the charge stored in the capacitor disappears. So what does this refresh really mean? What this means is periodically we come to check what is stored in the transistors. If it is 0, we don't need to do anything. But if it is a 1, that means there is some charge in capacitor. We need to put in more charge to, to make it full. So the charge keeps on decreasing over time. After a particular interval, we go back and fill the transistor again with charge so that it retains its value for longer duration. Okay, now we know how SRAM and DRAM store a single bit of information. But memory is not just a single bit of information, it's multiple megabytes or gigabytes. So let's see how we build such a big memory using the memory cells that we just saw. So this is a schematic that shows a 2D storage array. And what this array really is, it's a bunch of cells. In this case, what we are showing are DRAM cells. So to access data from this DRAM cell, what we need to do is, first of all, let's talk about the read access. What we do the first of all is there is an address coming from the processor. This address is stored here in this address register. Then this address is divided into 2 parts. The most significant bits, they represent the row address, and the least significant bits, they represent the column address. Then this row address is decoded using a row decoder, and what it tells is out of many rows in this array, which one do we want to access. And based on these bits, one of the rows is activated. What that means is all the cells in that row, for example, all of these cells are now activated. We are reading the value stored in all of these capacitors. Okay, uh, we read this value and take this value out of these cells. We amplify the values that we just read because the charge in some of the capacitors might be lowering down, so we need to amplify that so that we have a clear indication of where is a 1 and where is a 0. Now this row might have 1k to 4k bits depending upon implementation, but we don't really want to read all of these bits together. We only read maybe 64 bytes of data from DRAM in one access. So to select those 64 bytes among these 1k or 4k bits, what we need to do is we use a column decoder. And the column decoder is fed by the lower significant bits of the address or the column address. And based on this address, we choose our bits of interest. For example, in this case, we might want to choose only these bits and discard all other bits. So this is how we read data from a memory, which is 2D array of 2D array of individual storage cells. Okay, so let's compare the characteristics of SRAM and DRAM now. So as we have already seen, DRAM is slow because it stores the charge in a capacitor. Accessing a capacitor is slow because of its RC delay curve. Whereas SRAM is much faster because it does not involve any capacitor in storing the data. On the positive side, DRAM provides higher density because it only needs one transistor and one capacitor to store a bit. Therefore, in a given area, we can store more bits. SRAM, on the other hand, provides lower density because it needs 6 transistors to store one bit, which means we can store lesser bits in a given amount of area. Cost-wise, DRAM provides lower cost, which means for a given amount of money, we can have more amount of bits in our memory. And SRAM is higher cost because of the process technology that is used to build SRAM. So this is not suitable for building big memories, only for small ones. Then DRAM requires a refresh because the capacitors are leaky, and this refresh, it needs power because we need to put charge to the capacitors to bring it back again to a high value, and it also requires some area. Also, when we are refreshing a row in the DRAM, we cannot use it, or the processor cannot use it to read the data. As a result, it also reduces performance, whereas SRAM does not require any refresh.